Hello everyone, Shauna here with your geometry overview for this week. This video is going to feature an overview of chapter 5, which is similar triangles. And I'm going to begin to share my screen at this time and remind you of some of the things that we've talked about in chapter 5. Something that I want to make you aware of that I have seen recently with a homework and the quizzes is some of you are not following instructions. Please make sure you read the instructions about the number of decimal places you're supposed to carry, about the way that your homework is supposed to be submitted, with the highlighting, with the proper headings at the top of the page. Please make sure you're doing that. If you need help with that, there is a video check-in that tells you exactly how to submit your homework and a little bit more about those instructions. But let's not take too much time with that. Let's go into chapter 5, similar triangles. So in 5.1, we were talking about ratios, rates, and proportions, which is not that difficult. We talked about how ratios are two equal fractions, two equal quantities, and that the cross products in a true proportion, the cross products are equal, or we say the product of the means is equal to the product of the extremes. And using this kind of proportional technique lets us solve a lot of different kinds of problems, including the best price, the unit rate, and a lot of other things like this equation in example 5, where you can cross multiply once again, x times 56, or 56x is equal to 7 times 72, then divide both sides by the coefficient of x to get 504 divided by 56 is equal to 9. And that's basically the crux of 5.1. 5.1 is really a setup to help you with the rest of the sections. Now I'm going to go into 5.2 if I can here. 5.2 is about similar polygons, and we learned about similar triangles and other similar figures. And you learned also that in similar figures, the corresponding sides are proportional, and that big deal with similar figures. So in 5.2, we have the idea, like I said, of parallelograms and kites and different figures that we learned there. So once again, the big thing to remember is right here on slide 6, two polygons are similar if and only if every pair of corresponding angles have the same size and the ratios of corresponding sides are equal. Okay. Remember, this applies to any kind of similar figure, similar triangles, similar rectangles, whatever it might be, but they are similar. And you're going to have applications of similar figures throughout the rest of the chapter, okay? So be sure you understand what similar figures mean, and we're going to go through some of the other theorems that we talked about. One of the examples that I wanted to bring to your attention is this example here. Tyler wants to find the height of a telephone pole. He measured the pole's shadow and his own shadow, and then he made a diagram. Find the height of the pole. This applies if you have a pole, if you have a building. So you'll notice here, his height is one side of the triangle. His shadow is another um, hypotenuse. The height of the pole and then the shadow cast by the pole. So if you look on the next slide, you see how the similarity works. So we have 3 feet 4 inches, which is the length of the shadow, is equal to 460 inches. 7 feet 8 inches, which is the height of the length, I should say, of his shadow, and 5 feet 9 inches is 69 inches. So H, the height of the pole, over his height, 460 inches, corresponds to 69 inches, which is 5 feet 9 inches, over 92, which is 7 feet 8 inches, the distance from A to B. And then you solve and you find the height H of the pole. So make sure you study that. Similar triangles, finding a height. That is a very important concept and we use it a lot. That's the end of 5.2. Now, next section we had was 5.3. So let me bring up that section so we can look at that again. 5.3, proving triangles are similar. And these we had the similarity theorems for. So we're going to run through the similarity theorems AA, SSS, and SAS. If you need more help with what these mean, you can go back to the video. But 5.3, we talked about side, side, side similarity. Let me put up an example of this. So here we have side, side, side similarity, example 3. And then we have side angle side similarity as in example 4 right here. And then we have angle side angle similarity. And here we have also another similar triangle situation. So we not only have to use what we know about angle side angle and side side side, but we also have to use the ratios and proportions that we're going to be dealing with. So pay attention to that. Okay. In 5.4, we start to get into some other triangles. This is the stuff that you studied last week. Let me bring up that section here for you. In 5.4, we talked about the Pythagorean theorem, and there's something that I want to draw your attention to there. So let me wait for the PowerPoint to load, and then share the screen again. Here is 5.4, and you want to pay special attention here. The PowerPoint's open with 3 theorems. You want to pay special attention to Theorem 2 and Theorem 3. So here we're talking about taking a right triangle and splitting it down the hypotenuse and making 2 right triangles that are similar to the original. So we have the length of the altitude of the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. And so the length AB, the length of the altitude to the hypotenuse, so the altitude CD to the hypotenuse AB, the length of the altitude to the hypotenuse is the geometric mean of the segments. So if you take the geometric mean of AD, as in David, and DB, you take the geometric mean of the 2 at the bottom, it's related to the length of the altitude of the hypotenuse. And we have that theorem, and we also have theorem 3, which is the length of each leg of a right triangle is the geometric mean of the length of the hypotenuse and the length of the segment adjacent to that leg. So study those 2 theorems. You have examples. Example 1, pay special attention to example 3 and example 4, okay? Where we talk about the Pythagorean triples and the right triangles. Example 3, let me get us there. Find the Pythagorean triple for P5, Q3, and find the triples for that. So you can have 2PQ, and you can have P squared minus Q squared, and B is P squared plus Q squared. So you can find Pythagorean triples for that. The next example was example 4. And that was, let me go back a screen. That was determine the type of triangle. Do I have a right triangle? Do I have an isosceles triangle? What kind of triangle do I have? And so, and basically, we're looking for the type, and this goes back to the theorem, okay? So if you know that you don't have, you have 3 figures that fit. Remember, the longest one is the hypotenuse. So like C15 squared is equal to the sum of the squares of the other 2. If you have 6, 7, and 8, if 8 is the hypotenuse, 64 is not 36 plus 49, so it's not a right triangle, but 8 squared is less than the sum of the other 2, so you have an acute triangle. And if it's greater, if you square the longest side and it's greater than the sum of the others, then you know that it's obtuse. Okay, so that was section 5.4. Now we have more sections in the chapter. 5.5 and 5.6, and I'll show you those because those are your new sections for the week. So bear with me for just a couple of minutes here. I'm going to go ahead and load this up. These are the new sections, but I wanted to take the opportunity to go through this because there is a quiz on chapter 5, and it covered all of that material. So I wanted to make sure that I cover that. Let me. Another thing that I wanted us to pay attention to was in section 5.5, talk about special triangles. You might remember those are primarily the 30, 60, 90 and the 45, 45, 90 right triangles. And in that particular ratio, remember that for a 45, 45 right triangle, that the legs are the same length and that the hypotenuse is the length of that leg times the square root of 2. That's the length of the hypotenuse. Those relationships come in very handy when you're solving right triangle relationships if you're solving for the lengths of the sides. So make sure that you go over that. And also, let's look at the 30, 60, 90 right triangle that is talking about those relationships. So let me show you that. Refresh your memory there. So again, the side opposite the 30-degree angle is the shortest. The side that is the hypotenuse will be twice as long as the side opposite the 30-degree angle. And the side opposite the 60-degree angle is the length of the shortest leg times the square root of 3. Okay, so give that a little bit of a perusal. And I know that we've been over that in other videos, so I'm not going to belabor this point. What I will do is I will do one more thing here. I'm going to pause the record. I'm going to pick up with our last section, which is our new section for the week, and that is section 5.6, and it is divided proportionally. So we have points. Here's an example of what I'm talking about. Points D and E divide segment AB and segment AC proportionally. If AD is 8, DB is 14, and EC is 12, find AE. So in other words, we know that AD and DB are in the same proportion as AE and EC. So if we look at this, we can see that you don't need to have just one point. So we can go back to example 1 again. And we'll look at the solution for this. AD and DB equals AE over EC. 8 over 14 is AE over 12. And so once again, all that basic algebra from 5.1 comes back right here. And all of those things that we know about similarity come back. So we have that. We also have the numerator denominator addition property, that if I add a number to the numerator and denominator to each other, then the original fractions AB and CD are equal. You can read more about that on your own. There is another theorem here on slide 7. If a line is parallel to one side of a triangle and intersects the other two sides, then it divides these sides proportionally. So again, there's a proportional theorem for you. There's a corollary to that theorem as well. And I wanted to pay special attention to example 4. And this is relating to the angle bisector theorem. Remember, to bisect is to cut in half in equal parts. If a ray bisects one angle of a triangle, then it divides the opposite side into segments whose lengths are proportional to the length of the two sides that form the bisected angle. What does that mean? That means that in this case, AD and AC are proportional to each other. The side that is bisected is proportional to the side that it actually begins on, and DB is proportional to CB, again, only if you bisect the angle. Okay, there's an example of this in example 4. So I can use that to find sides of a triangle. For triangle XYZ in the figure below, XY is 6, YZ is 10. If YW bisects angle XYZ and XW is 2 units, find XZ, find the whole length. So we know that XW is proportional to XY and ZW is proportional to YZ in that case. So 2 over 6 is proportional to ZW over 10, 6ZW is 20, and ZW is 20 over 3. But now 20 over 3 plus 2 is the full length of my segment. Okay, so pay attention to that. We have some other examples for you of that, and this has been we do have another theorem here on slide 15, Chaves theorem. We don't use it that often, but it is pronounced there, and it is used. It has to do with points on the interior of a triangle, and they have to do with the product of the lengths of the sides. It's not as common as some of the other theorems, but I'm going to go ahead and stop this review right here. I hope that's helpful to you to see this. I hope that it will help you in studying for your chapter as you put it together. And I I wish you the best of luck. Remember, follow the instructions. Pay attention to the number of decimal places that you're expected to use. And please read the announcements and other important notifications from us. Best of luck, everyone. I hope you're all safe. I hope you're all well. Take care, and I'll see you in the next video. Thank you very much.